In this video, we'll talk about different things to keep in mind when you're trying to solve problems using integration by parts to make sure you stay on the right track for these solutions. So what should you do when you see a problem that looks like integration by parts to analyze it and solve it in the appropriate way? Well, your first thought should be if you see an integral that is an integral of a product, that maybe integration by parts is the way to go. You'll likely want to check at this point to make sure it's not a substitution problem, that by doing an appropriate substitution, the product part goes away. But once you check that and you see yourself with a product, integration by parts is probably the way to go. So you basically need to pick what u and dv need to be for this problem. So you need to visualize this product as a u times dv. And what are the key points here? Well, we need to be able to integrate directly the dv term. Right, I need to know what the function v is from dv to be able to solve this problem. So if I can't directly integrate that term, it's not a good choice for dv. The second half of this is ideally when you go to then the v du integral, that should be simpler than the one you started with. I'll switch it to saying no more complicated because there's an example that we'll do in the next video that illustrates this point. But you want to seem like you're making some sort of progress towards your answer, that somehow the new integral you get is easier than the one before it. What are some sort of more direct pointers towards this end? Well, the first is you want to differentiate inverse trig and logarithmic functions because we currently have no way to find their antiderivatives. Given you don't have any of those, you will then want to differentiate polynomials because polynomials will go away after enough differentiations. And then your last thought is exponentials and trig functions. Those are usually fine to either integrate or differentiate because we have formulas for them going either way. You can usually do whatever you want with those functions. So let's see an example of what this might look like. So we want to find the integral of x squared sine of x dx. Now if we think about back to our rules, I don't see any logs or inverse trigs, but I do see a polynomial. And so I should think about differentiating the polynomial, i.e. making that u, so that it will eventually go away after enough integrations by parts. So let's set this up and see what I get. So I want to set u to be x squared. So then du is 2x dx. To make this setup work, I need dv to be the rest of my expression. So dv is sine of x dx. So then v is minus cosine of x. It is the antiderivative of sine of x. And now we can write our formula. So integral of x squared sine of x dx should be u times v, which is that, minus the integral of v du. I'm now going to simplify the expression a little bit, so I get the minus x squared cosine of x, and then plus the integral of 2x cosine of x dx. Now we're not done yet, but this new integral is better than the one before it. I've gone from having an x squared term to an x term. If you think about it, do this one more time, the x will then go away and be left with something that I can actually solve. So let's do this one more time. I'm going to set u to be 2x, so du is then 2 dx. I'm going to set dv to be cosine of x dx, so then my v is sine of x. And I can do integration by parts one more time. So I keep my negative x squared cosine of x. I then add in the next u times v, so 2x sine of x. And then I subtract the integral of v du. That last term I can now integrate directly. Sine integrates to minus cosine, and that minus will cancel this minus sign out in front. So what I will get left over at the end is a negative x squared cosine of x plus a 2x sine of x, and then plus a cosine of x with a 2 in front, plus c. So that's what I will get for the antiderivative there. And if you differentiate this, you will in fact get x squared sine of x. So important facts here are you can do this process more than once. It's entirely possible to integrate by parts more than once to solve a problem. And if it's going to take more than one step, you should see at least some progress towards your answer as you go. Your resulting integral should get no harder than the one you had before. In this case, we saw an x squared drop to an x term, giving us hope that one more step would make it go away. So here's sort of the thought process you can go through when you're trying to pick what to do for integration by parts and how to pick which term should be integrated differentiated so that you can solve these problems quickly without getting lost in the mess of these loops of integrals that don't seem to go anywhere. So as long as you follow these rules, you should be on the right track to figure out how to solve these problems and get these right answers using integration by parts to solve these integrals.